Thank you very much for the introduction. Hello, guys. My name is Wenchao Zhuo. I'm from University of Arkansas, and as you can see from the logo, we have founded a lab called AM3 Lab here, short for Advanced Manufacturing Modeling and Materials. So today I'm gonna, hopefully get you all excited about 3D printing. Hopefully you're already excited about it. So I'm gonna talk about 3D printing as a method for future of manufacturing. And the subtitle is the fourth wave of human civilization. So we humans have a very humble beginning, and we started from a nomadic lifestyle. We don't have any stable food source. We don't have a fixed residence. We have to hunt for food. We have to move around. And then about a few thousand years ago, we have the first wave of technology revolution, which was agriculture. And it gives us a stable food source, and so that we can live at a fixed residence, so that we don't have to be nomadic anymore. And then it comes the second wave of technology revolution, which was about 300 years ago, the industrial revolution. Previously, we still have to use our own labor to produce, to feed ourselves. But after the industrial revolution, we have been able to use machines to do all these things for us, and which freed us from labor. But there's one catch, which was that there was very little individuality. Everything had to be mass-produced, and it was produced in factories, and it was very capital-intensive. You pretty much get out of hand of individual human beings. And the pace gets faster. A few decades ago, we have this third wave of information revolution, which gave us the personal computers. And this is the democratization of information. And a lot of technical geeks can just get together and start a company by their own, because it requires very less capital. And you can basically become a hero by programming and software, and that's being adopted by the masses. So it gives us great individual freedom. We've been able to receive information and give information on an individual basis. So we have these three great revolutions that have fundamentally changed our lifestyle. That keeps us wondering what would be the next. So what would be the fourth wave? So we have this personal computing age. We have all these personal devices, unprecedented individual power. But everything is all limited in this virtual screen. It doesn't get outside of it. We still sometimes feel powerless. And as human beings, we're always makers. Since very beginning, is what differentiates us from animals, because we can make tools. And however, for nearly half a century, everything is kind of moving to the modern factories. We don't see how things are made anymore. And we haven't been able to say how manufacturing happens for generations. So this brings up, the next change that we want to make, which we can make an analogy to personal computing, which we call it personal fabrication. So in this age, we envision that we're going to have some factories that's sitting on our desk, and we can basically make anything that we can design from a computer screen. And in this way, we can truly get, the individual power we want. Because we won't have any individual power, unless we can make. We can really make things happen to get into the physical reality side of it. So how do we go about personal fabrication? And my answer is that it actually resides in a ancient technology called printing. And we're very familiar with printing. It was invented about 2,000 years ago in China, the woodblock printing method, which is actually the original technology that brings knowledge to the market. And afterwards, we invented a mobile type, and in 1951, we have the first digital printing technology, inkjet. And in 1984, we extended to one more dimension. We get a 3D printer. And in 2012, this is a picture that was drafted by the Economist magazine, which you can say people sitting behind the desk and all these great things coming out of it. And this is the future that they were looking at. So many people probably don't know printing is actually a very big industry. It's actually the biggest industry in the world. And it outshines the music industry, the automotive industry, and with an annual GDP of about $640 billion. And we print about 45 trillion pages every year. So if we can extend this printing to 3D, imagine what we can do if we can print 45 trillion objects every year. That would be truly the age of personal fabrication. So this is what we say in the paradigm shift in printing technology. The first paradigm shift is going from the traditional printing technology to digital printing technology. Right now, there's only less than 10% of printing that's done by digital printing. A lot of them still using, the screen printing or the rotary printing, the traditional printing method that requires a mask, so that everybody still get the same thing. But if we go digital, everything is going to be different. So the second paradigm shift is go from graphic patterning to material patterning, which is basically manufacturing. Because manufacturing is how we pattern materials into different shapes and functionalities. So these two paradigm shifts will help us to get into the age of personal fabrication. So what's the motivation for this paradigm shift? First of all, digital is great. Digital is what every business wants because it's on demand. It has zero waste. You don't have to stock anything. It's decentralized. You can distribute it anywhere in the world, and it's easy to store. It's green. It's easy to distribute. Easy to use. It's clean, and it has very fast turnaround. Because one of the things that business hates is uncertainty, and the digitalization can help us get rid of these uncertainties, but by streamlining the processes. So for material patterning, if we can digitalize information, and wouldn't it be better if we have actually a digitalized world? If we can actually have a digitalized object, and 3D printing can hopefully become a tool for it. And it gives us cheaper, faster, and better products. So this is the evolution that I say. And we have the mass production from the Industrial Revolution. And we have another digital revolution which brings us the customization of information. We can customize the information you send and you receive. And if we can make the digital patterning work, the digital fabrication works, we're going to have a digital industrial revolution, which is going to give us mass customization, which means everybody is going to get customized parts at a cost that's no more than what we're currently paying for. So this is a map for the manufacturing technologies that we have developed, over the history. And we have on the x-axis here is the object size. Is the relative accuracy. The y-axis is the object size. As we can say, For very large objects, we're still relying on, traditional machining for manufacturing. For very small objects like the CPU you're using, or, the sensors in your cell phone, all these small devices, we have invented the MEMS and NAMS technology to fabricate those. And what additive manufacturing stands is actually in the center. It's mostly for micro and meso scale manufacturing. And it's very difficult to fabricate very large objects with additive manufacturing. And it's also very difficult to fabricate very small stuff with additive manufacturing. So if we truly want a personal fabrication, and one of the first things that we need to overcome is, can we actually digitalize all this information technology, and so that and to make it at a cost efficiency that's comparable to traditional manufacturing. Otherwise, it's going to be hard for people to accept it because of the high cost. So one of the difficulties for replacing traditional manufacturing is that all of the 3D printers right now is too slow. And we know time means money. Manufacturing time is what determines its final cost. So that means if you want to mass produce some products with additive manufacturing, it's going to have very high cost. And it's very difficult to print very large size because additive manufacturing technology is very hard to scale. And if we want to replace MEMS or LAMS technique for making CPUs, we will not only need to make them fast, we also need to improve the resolution as well. We want to get into the nanoscale. So we have all these challenges that stand in the way for us to get to the age of personal fabrication. So this is why we founded the AM3 Lab at the University of Arkansas. And our primary mission here is to develop ultra-fast 3D printers so that we can decrease, the manufacturing cost by increasing the printing speed. We want to be able to reduce the printing time from currently hours to minutes or even seconds. And we want to make this fast enough so that you can compete with traditional manufacturing for mass production in terms of cost efficiency. So the second mission of this lab is that we also want to promote the use of additive manufacturing by exploring some cutting-edge applications. And we're developing some new applications on 4D printing. We're also working on some new 3D printable materials. So I'm going to briefly go over, these different projects that are ongoing in our lab. Hopefully, it can inspire you to come up with similar ideas and to contribute to make the personal fabrication happen in a short time. So one of the projects that's ongoing is the inkjet printing technology. As many of you probably have known, you probably own an inkjet printer on your desktop for 2D printing. And it can also be used as a very elegant 3D printing technology because it has a wide choice of materials and it's very easy to scale. It's digitally controlled. It has very fast and no cost operation. And it naturally integrates multiple materials, just like you're printing multiple colors. And it's clean. So that's the two most common inkjet techniques. We'll call it drop on demand because you can produce a droplet anytime you want on demand. So one of that is using a piezo transducer that when you apply a AC voltage, it deforms a membrane which ejects the droplet, as you can see on this left animation. A second way is what's being used typically in HP and column printers. They use a microheater, a very small heating device that heats up the ink and produces a bubble, and that bubble, produce some kind of pressure to eject the droplet out. So one of the problems with this inkjet technology is that you print at about a speed of about 100 cubic centimeters per hour. it's very slow process. If you want to just turn it 100 cubic centimeter cube, it's going to take an hour, which is not economical. And it produces droplets at about 10 kilohertz in terms of frequency, which means for every nozzle, and you can have an array of nozzles for each print head. You can have as many as 10,000 for even more nozzles. But for each nozzle, it produces about 10,000 droplets every second. It sounds like a lot, but if you just do the math, you'll find the volume of droplets is not actually that good because the droplet is very small. And if you think about the 600 dpi printer you get for the inkjet printer, the droplet size is typically around 50 microns. So that gives a very low speed. So what we want to do is to improve this printing frequency by 100 times. We want to get to megahertz inkjet printer. And if we can do megahertz compared to kind of 10 kilohertz, we can actually improve the speed by about 100 times. And this problem is actually very, very challenging problem. It's a very old problem because the fundamental physics resides in the droplet breakup, which has been studied since the age of Newton. And so what we have done is that we have come up with a hypothesis that if we increase the jetting speed, we can hopefully overcome this lateral limit, which is limited by the surface tension force. And it's very difficult to increase the surface tension force to increase the turning frequency. So what we did is to increase the jetting speed, and we have done some simulations which shows we can improve the turning frequency to megahertz for sizable droplets. So along this line, we have also studied some other aspects of inkjet, and one of that is droplet deposition. So when the droplets come out of a nozzle, we want to be able to see how they evolve and form different patterns. And it turns out this is very computationally expensive, and the kind of computational commercial software cannot simulate it. So we developed a experimental validated numerical tool that can help us simulate this whole process. As you can see on the left side, we show an animation of several droplets interacting together. This is actually the first time this is done. So it runs about 100 times faster than commercial software, and which enables us to simulate this droplet deposition process. So to along this line, if we want to actually produce a super fast inkjet printer, we also need to work on the inkjet print system, which we have been started working on it. One of the idea one of the motivation why we do this project is because the current 3D inkjet printer is very costly, and it costs about over $100,000 for you to buy any of the 3D inkjet printers on the market. So we want to build a low-cost solution. And this is a printing system that we have developed, and we basically disassembled it from a Epson inkjet printer, and we use the inkjet printer head to print. And we construct the XYZ stages so they can become a 3D printer. And the whole system is not finished yet, but hopefully we'll get it done, in the next couple of years. So a different process that we're working on to improve the speed is to improve the selective laser melting process. So if you are familiar with this process, it's a process that uses laser to scan over a powder bed, like what's shown in this animation, to melt these powder particles, join them together, and build it up layer by layer. And the problem with this process is that, the laser is too expensive, and it's hard to maintain. And the second is the laser is too energy, inefficient. And the third, which is our point, it's slow because it's a point-by-point scanning process. It's very difficult to speed it up. So I cannot talk too much about, our current solution yet in a lot more details because everything is still in a very early stage. But I will briefly give you an idea of what we're doing. So what we're doing is to develop a inkjet-like print head, which is kind of scalable using kind of multiple nozzles instead of one single point. So you can print a whole layer at one time. And based on our calculations, about 100 times more energy efficient than laser. And because it's scalable, we can hopefully, to scale it to a very high speed. So this is some of the results that we have gotten in developing this print head and to make this process happen. It's a MEMS device just like an inkjet print head, and it's multiple layers, and this is the print head design, and this is the design of our packaging. The center chip is the print head that we're developing, and this is the silicon wafer that we use to fabricate a print head. On this silicon wafer, we have 16 different print heads on it. So again, everything is still in a very early stage, and hopefully we'll be able to talk more about it in the near future. So another different problem for this active laser molding process is the powder fading process. And you have this wiper that wipes across this powder bed to spread a layer of powders. And it's actually a very slow process because the wiper needs to accelerate and wipe and then decelerate and stop and then change direction and do it again. So it takes about a second to spread one layer. And if you are going to do thousands of layers, it's going to be hours. So our solution is that we are developing a new powder fading system that can potentially reduce the powder fading time. And this is a design of our powder fading system, and we have tested a test set up to say the spreading quality of this design, and this is some test results. And also this because our lab is fairly new, so everything is still in a very early stage. So one of the things we want to do for these different processes is that we actually need a lot of MEMS device, the micro devices for the print head. Say, for example, for the inkjet print head, it's a MEMS device. For this new process that we're developing, print head is also a MEMS device. So we're thinking, we're a manufacturing lab. Why do we have to rely on a clean room to do this? So, this is why we're developing this nano printer. We want to be able to have, a self-sufficient lab, and so that we can just print these devices that we need with more flexibility and no cost. So this is another printer that is designed to achieve sub-micron resolution. And it sits on a optical table to isolate the vibration at very high precision motion stages with a nozzle size of about 100 nanometers. And we have also developed a software which you can save from the computer screen to control this printer so that you can input a STL file and print three-dimensional features with it. This project is 70% of finished, and we're still working on it to perfect it. And this is some test printing results that we get. We're still having some issues to get the printing line width to conform with another size. This is a print testing of a line with a 10 micron nozzle tip. As you can see, we get about 80 micron line width, which which is still not ideal because of some issues that we're experiencing. But one thing that we do get is the thickness. The thickness of a printing line is about 200 nanometers, which we're printed using silicon. So, and the surface roughness of the silicon is about 40 nanometers. We do airframe scan. I forgot to include a picture here. But this is, some promising results we have getting from this nano printer, which you can hopefully help us to produce some nano features. And this is an animation of how this nano printer is working. And as you can see here, there's still some issues we try to figure out. So that was, our mission of developing the 3D printers. And we're also exploring some of the new applications for additive manufacturing. And one of the exciting fields is 4D printing. And 4D printing is basically 3D printing plus smart materials. Smart materials are some kind of materials that can respond to external stimulus. Say, for example, if you change the temperature, the materials can change its shape. And you have some immerse in water and you can change its shape. So by knowing how the material is going to respond to the external stimulus, we can design a structure that can respond to external stimulus. We can basically program the structures beforehand, before we print it. So this is what's known as 4D printing. The additional dimension is time. So this is some, on the left-hand side is some research results from the MIT lab. They have printed a hydroactive polymer, which if you immerse it in water, it slowly grows into a pattern that shows MIT. And so we want to continue working on this direction because we see a lot of potential. One of the things that we want to work on is software robotics. So we know there's a lot of applications with robotics, but one of the downsides with the current robotics is that it's rigid. And this rigidity makes it, unable to adapt to uncertainty. And, in contrast, our humans, we are soft. We have, very soft hand. We can grab different sizes of objects just because our hand is soft. So what we want to work on is to 4D print software robotics, and so that you can adapt to uncertainties in the future. Hopefully, we can print a whole software robot. And one of the materials that we're trying to work on is called dielectric elastomer. And this is a material that's kind of very interesting because it has very large strain and very large stress. It has very large strain energy, and it can produce very large strain. And the strain energy that it has is about 100 times more than human muscles. So that means, if you print a software robot with this material, you can hopefully get 100 times stronger than humans. And so this is why this material is called artificial muscles. It has already been studied to be 3D printed. So this is actually one of the focus that we're working on. And as you can see, the motivation is that we want to explore the frontier so that, in the future we can directly print some software robotics. So one of the things that we get started is to print some kind of actuator, right? So this material is behaving like this. You have two electrodes on two sides, and you have this dielectric elastomer, which is thin film, a membrane, and sandwiched in the middle. And when you apply electricity, when you apply voltage to the electrode, there's going to be electrostatic force, which is attracting the two electrodes on the two sides. and this force will compress the membrane in the middle, and this membrane will expand. It will be compressed in Z direction, in the thickness direction, but it will expand in XY direction. So this is actually where you get the actuation. So this is some of the samples that we have trained, and this is a circular shape dielectric elastomer actuator, and this black thing in the center is the electrode. This gray membrane is the dielectric elastomer. We have also developed a different configuration. So this is a test of the actuation. You can say when you apply voltage, the edge is deforming on this side. So we can design different configurations so this can become a linear actuator. When you have a linear actuator, you can get into more complex motions. One thing that's needed for actuation of this dielectric elastomer actuator is that it actually requires very high voltage to actuate it. It actually requires thousands of volts. And that's why we developed this high voltage supply system to actuate it. And you can go up to about 30,000 kilovolts to drive this actuators. So for this all to function in the future, we have to be able to bring down this voltage supply to a few volts to be safe to humans. And one of the key critical things that we can do to reduce the voltage requirement is to reduce the thickness of the membrane. And right now, the membrane that we're using is about 200 micron thickness. So since we have already developed the nanoprinter in our lab, and this is going to be our next step to do. If we can reduce the thickness from 200 microns to 200 nanometers, we can hopefully reduce the voltage requirement by 1,000 times, which is going to only require a few volts to drive this, which means you can use a battery to drive this actuator. So another different project that we're working on is to develop a new 3D printable material. And we're working with the company locally here on this magic material. This material is transparent. It feels like human flesh. And its hardness can be adjusted by changing the recipe. But right now, it's mostly produced using molds, using hard molds to produce it. It's a thermoplastic. So we're developing some printers that can actually print this material. If this material can be made 3D printable, it's going to have huge applications in multiple fields, such as the medical field. And then there's a huge attention on how to get flexible materials 3D printed. And hopefully this is going to be one of the interesting projects to the whole 3D printing community. So this is pretty much what's going on in our lab, and I would be happy to take any questions if you have any.
All right, how close are you to getting that human flesh material printed? Like, how long do you think we can expect to see that?
It's very close, and hopefully in the next few months.
That'd be very nice. Do you think you can get that to market, or would that be something the universities could collaborate together to get?
Yeah, that's actually one of the plans. We hope to commercialize this if everything goes well.
Excellent, excellent. I was designing a human hand that could actually use a flesh material on it, so I'm very interested. Thanks.
Yeah, if you're interested, hopefully you can. If you get some time, you can come to visit the lab to stay touch the hand.
Let's give a hand to Dr. Zhuo.
Thank you, Dr. Zhuo. We will be in touch. Thank you.
Thank you very much.